Okay, so question 17, we have a charge is moved through two different paths in a uniform electric field. There's a change in potential between points A and B, greater than, less than, or equal to the change in potential between points A and C. So what's sort of nice about this question, again, it highlights that we can answer this question without knowing the sign of that charge or its magnitude. So the change in electric potential is only a property of the electric field and the distance between the 2 points. Really, it's technically the dot product between these two. So that's that's how I'll use this question, and that's the concept I'll use. So delta V is technically negative E dot delta X, and you've seen a similar. You would have seen a similar analysis of this if I write down here. Sort of extra notes. So we defined the work back in mechanics course, your 114 course, as F dot delta X. So you're looking for how much of the force is in the same, to calculate the work, you're looking for how much of the force was in the same direction as the displacement. So in that case we define this sort of as F delta X cosine of theta, and I'll do a similar analysis in this particular problem. So we can see that the electric field points to the right, and there's in a sense a delta or. It's not technically in the x direction, but a delta or. But I'll look at the components that are basically either in the same direction or opposite direction of the electric field. So let's just do A to B. So if I think about the A to B case, and I'll try to draw this accurately on my ruler here. So the electric field vector will point to the right. Maybe I'll make it 3 centimeters long, and the displacement here, let's go with 4 centimeters at some sort of angle for B, from A to B. This is A and this is point B. And to find, in a sense, the dot product or scalar product, we're looking for how much of that particular displacement vector or E vector is in the opposite direction. So we're looking at this component. So if this is the, we could consider this the angle here, theta, and I consider that delta V is equal to negative E times the delta or from A to B times the cosine of that angle theta, which gives us some number. Now if I bring this sort of down here and show you that we end up with the exact same answer for A to C. So again, the field is a uniform field, so again I'll draw my E field has the exact same size. Now what you'll notice here is that the x components of these displacement vectors for A to B and A to C are exactly the same, but it's just in a sense steeper for C. So I'll try to again draw my best diagram here. So it might be further away in direct distance, but all that really matters is the component that is sort of parallel to the E field, which are identical. Okay, so these horizontal dot lines are the same. So if I label this as V, the delta V, this is I guess A to B, this is A to C, negative E, which is the same here. We've got the delta R from A to C times the cosine of phi, but the delta R A to C cosine of phi is the same as the delta R A to B cosine of theta. So their x components are the same, so we get the same change in potential. And this is sort of a base, going back to sort of first principles and thinking about how the change in potential is a function of the electric field, and or again, since the delta V between 2 points is dependent on the field between those points and the displacement. But you could, I guess, this could have answered this question a little bit quicker if we sort of think about equipotentials. So equipotential lines are always drawn perpendicular to the field. So we can draw an equipotential line for that point A lies on. Sorry, I sort of drew that kind of crooked. It should be exactly perpendicular to the field lines. And then notice that C and B also lie on the same equipotential. So in moving from one equipotential line to another, we've got these are not the same equipotential lines, but any point that lies along sort of this line here, lies to the right, at the same potential. All points that lie along the line on the left have the same potential. So I could state that VC equals VB, because they're on the same equipotential line, lie on the same equipotential line, which means that the VA minus VC is equal to VA minus VB, and vice versa. C minus VA is equal to VB minus VA. So the change in net potential between the 2 points is definitely equal to each other.